All right. All righty then. Oh man, I need some headphones. Actually, you know what? I don't even need these. Oh, there we go. Wait. All right, this actually keeps me up in the chair. This is why I like this. And I can't get it to stay. Maybe, do I get two? This is fucked up. Oh, there we go. I gotta do it on the way up. There's only like 2 spots where it can be, I think. I really just want to feel like I'm moving up. That's the lumbar support. Okay, this is actually good. This lets me feel on my... What the fuck is going on here? There we go. That's a little bit better. Okay. Now that I've settled that. All right, let's talk about some voxels. What up, man? I've been up, been cleaning up my office. Or trying to, at least. I mopped and vacuumed and all the good stuff. So earlier in the series, I was doing stuff like this. I was gonna do this series. So we're on day 13, goals. So for today's goals, let's do noise. Noise, chunks, and blocks. Generation, question mark. We'll just do basic world generation. Okay. Oops, don't need to save this. Let's talk about some noise. So these are our goals here. I probably can put it in the corner up here. That's what I'll do. That's what I'll do. Let's see if I can add a window capture. We'll say with it Sublime. And let's filters. I wish that I could drag this. Kind of drives me crazy. That's lucky. 290. 75. 50. Whoops. And okay. Put it right above my head. Can you even see that? That's the question. Hopefully you can. Okay, so let's talk about noise and what it is and how it works, and it's so cool. So I'm just gonna bring. So noise is basically points it's randomization that this is complete layman's terms. This is me trying to describe it based on what I know of it. It's basically a way of, it's a deterministic way because it's always based on a pseudo-random algorithm, which a pseudo-random is going to give you, it's deterministic as long as you seed it, right? Because normally like a regular just random number will come from a random object that's seeded with like the date and time. That's normally, it's probably a little bit more complicated than that and secure than that, but that's the basis of it. But essentially what noise does is it gives you these peaks. It's random and it's in and out, but the thing that's nice about it is that it all goes together, right? So like if you gradually, it's like a gradient, it's like if you can picture like if you're looking at a flat surface, 2D surface, and the height is based on this randomization, it's got these peaks to it, this mountain, it gradually rises and then it also falls. And the thing is you can pick certain parameters for the noise of where to generate it, and it creates this nice, you can kind of see like how this grid right here has it like blocked off. Like basically you can go through your noise function and you can generate it for this block using, X, Y coordinates. And then you can generate it for this block, and these two blocks will go together. It creates this nice flowing pathway. That's why people use it for terrain. And it's also got a bunch of nice little things you can change that tweak it. It's based on a hash, which is this guy, and then it's able to create these gradients from the hash and use like a random, like I said, like a random value and a lerp, which this lerp stands for linear interpretation, or linear. What does lerp stand for? Linear. No, that's definitely not liberty. Wow. Lerp. Computer science. Graphics. I think it's linear interpolation. I was close. What did I say? I don't even know what I said. I said linear interpretation? What did I say? Did I say interpolation? It's early. It's not really early. I'm just drawing a blank here. Anyway, so it basically picks these points, these random points, and it gradually builds these peaks or these mountain looking things. This is 2D, right? Because I'm talking about basically if you're looking down the flat plane, but you got to imagine it from like looking down at it. You pick a X and a Y and it gives you a height back. So it's a 2D sort of. Give me 1 second. Yep, she can. Just send her out here. All right, love you. Okay, sorry for the interruption here. Oh, okay, so let's talk about it. So let's read what they've written about what actually noise is here. So Perlin noise algorithm that is often procedural content generation is especially useful for games and other visual media such as movies. The man who created Ken Perlin won an Academy Award. An Academy Award. Interesting. I did not even know this. The Technical Achievement Award. Badass. I didn't even realize you could do that. Anyway, if you're fortunate enough in the computer science world to create an algorithm that generates something that you can have the algorithm named after you, that's pretty amazing. And this is definitely a huge and widely used algorithm in games. In game development, Perlin noise can be used for any sort of wave-like undulating material or texture. So a lot of people say, so like, yeah, Minecraft-like terrain, which is what we're going to use it for. Fire effects, water, clouds. I've definitely seen it used for clouds. It's actually really neat. So I mean, we can talk all day about like basically how it works and the mathematics behind it all, but this is basically sort of the idea is that you get these points per your grid, and then you kind of linear interpolate to that point, and that point is based on some random value. So you get these nice waving hills and stuff like that, and you can use something called like 3D noise or simplex noise. I think. Let's see what simplex noise is. I forgot what that is. Simplex noise is a method for constructing n-dimensional Perlin noise. So 3D noise is, so if 2D noise is your hills, your mountain ranges, and your basically the top of your terrain, then you can imagine 3D noise as being tunnels underground. If that makes sense. Because 3D noise generates everything in a depth and a width, and so it's encompassed. It's not just a height. You get, basically, you give it a X, a Y, and a Z, and it's going to tell you whether or not that thing is underground. Open simplex noise. Look, it's covered by a patent. That's kind of crazy. And then here's open simplex noise. So in general, this is kind of what noise looks like. And this is not very high definition noise, but this is kind of what it looks like. And what's really cool is that you can give it you can pass certain parameters or certain like scales and focus, but like pretty much it's kind of like anti-aliasing works, where you kind of go around the detail and then you take kind of an average and you focus in, like it hones in on the detail. We can talk about anti-aliasing as well later. That's something that we'll probably want to do so that it looks nice and smooth. This is the other thing, this giant quadratic looking thing. So in a nutshell here, this is what we're going to be using. And we can, okay, so here are these parameters: amplitude, frequency. It's basically how, like, you can see you can get this really rigid with like high frequency and fairly high amplitude. And then you get these like super small mountain ranges. Then you can get these really tight, bumpy terrain. But like, we'll probably want something, yeah, kind of like this, probably. These like rolling hills. And you'll see how those kind of, here's improved Perlin noise. Let's see what this is up. Oh, official improved. Oh, this is Mr. Ken Perlin here. This is the real deal. Oh, crazy. He did it in, he wrote it in Java. God, that's so ugly. It looks like it just uses a new hash function. Let's use this. Let's use this. I like this. Let's use it. All right. So let's just add like a little math namespace. Let's just call this Perlin noise. Oops. Now, Perlin noise this is not the best. We probably want to call it. We're going to make changes to this, so we may rename this class to like. Actually, you know what? The simplex noise might actually be what. Open simplex noise. Oh, this one's got. Ooh, okay. We're gonna do this. We're gonna use this. Let me see what license this is. This is a free and unencumbered software release into the public domain. Anyone is free to copy, modify, publish, use, compile, sell, distribute. I'm trying to determine how I want to do this actually. Let's let's add this. It's going to be open simplex noise. We'll add it right here. It's pretty gross, to be honest. Looking at this code is just really nasty. Like, look at this. Gross. Let's get the namespace right. This looks like just a static. No, it just has a static. So let's figure out a way to test this. So let me see. I think I can use this system drawing. I'm not going to use it. All I really want to see is if can we I just wanted to see if we could write out like an image. But that might not be, if I was thinking it would be fast. Let's see though. I think we can just use a bitmap. Yes, I think that's what we want to do. Bitmap. I'm pretty sure. I don't think it's very difficult either. Bitmap. Yeah, let's do this. Okay. And then I think there's a save method. Okay. So let's do this as like a little test. So this open simplex noise. Let's open our main. Wherever the hell our main is. Here it is. And let's just come down here, and actually what we'll do is we will just remove this and this, and we will just try this little, we'll just do test noise, and then we'll write a little private static void test noise, and let's create a noise object, and we need to give it a new seed, so we'll do new random we'll give it a next. So we're just passing as a seed, we're just passing a random. It's not a big deal. But actually, you know what? Let's just come up with, because we want it to be deterministic right now. So let's just do like, let's do 1, 2, 3, 4, 5, 6, 7 as our seed. Excuse me. And then let's create a bitmap. System.drawing. Do bitmap, and I think we want, yeah, we just want, we'll just do 512 by 512. And let's see, 4. Actually, so let's see what's on this noise object. So we can get evaluate. That's all we get, actually. And we can pass an X and a Y. So let's do this, and then let's see how this looks. That was from the example yesterday. Let's close that. I wanted to pull up this other deal really fast. Wait, frequency. Okay. So let's set up some general junk here. So let's say this is, let's say we want this float, we'll call it amplitude. Oh no, actually we just want it to be a float. Amplitude. I want to figure out where we had this. Excuse me. 0.25 and 0.5, huh? Those are small little values. I guess let's do that then. Let's do 0.25f and then float. Actually, that's frequency. 0.25f, and this is 0.5. Amplitude, and then let's do, we'll do uint octaves equals 6. Okay. I wonder if I can do, so let's do pixel format, and let's do, I guess just RGB. Can I just do black and white? RGB, I guess. Whoops. This is system.drawing. What does it take again, damn it? System.drawing.imaging pixel format. Oh, here we go. (32-bit per pixel). Okay, yeah, that's fine. Let's do that. RGB 32, which just basically means we use the first 24 bits for RGB, and we do not use the last 4 bits. So let's see. Is this just as simple as like set pixel? Do I need a lock? Let's see what bitmap.lock does. Let's see, lock bits, I mean. Oh, lock, that's for says we're not gonna have anything else. This should be fine. So let's do this. Let's loop the octaves. So octaves are basically like your alias, your anti-aliasing changes. So what we want actually is, well, if I can find where it was. Yeah. So okay, we want to. I think we want to have a total here, and then for. This is where we start our loop through the octaves for. Whoops, for our octave, we need to do uint. Octave is less than octaves plus octave. Is it octave or How do you spell it? Let's see. I'm curious. I think it's an IV. Nope, it's an AV. Shows you what I know. Octave, octave, octave. Damn it. Fucking Windows. Why does it do that? Okay, so from here we want to excuse me. Where does A come in the picture? Okay. So our loop is just going to be basically the size of the image. And let's do this. Let's do like a constant width, and there's going to be 512, and constant height equals 512 as well. And then we'll make this width, make this height, and then we're going to basically do a loop here. So we're going to do an x equals 0. X is less than width plus x, and then for int y equals 0, y is less than height plus y. And then we're going to include our octaves. They're going to be inside each thing. So we're going to have a float. Mx is going to be x times our frequency. It's going to be y times our frequency. Sheesh. And then I think we want to get our, let's see, we want to use noise, evaluate. I think we want to get like a mx and y. Yeah. We'll just call this total. Oh, no, we already have one. Result, I guess. And then our total is going to be plus equals, I think we do math.max, math.min, because we want this thing to be from, I got to see what this thing generates actually first, but we want it to be between 1 and -1. And then this is times the amplitude. think this has got to be a float. Excuse me. And then at the end of each octave, I think we take the frequency and the amplitude, and we divide by 2.0. This is actually important. This needs to reset each X and Y. So let's see what this thing's giving us actually. So we'll do a console.writeLine. And we'll write out X as X, Y as Y, and then this is going to be equal to, and the value is going to be our total. And I think we need total to be 0 as well. Excuse me. We're not writing our bitmaps yet, but this will give us like an output. Actually, you know what? What? Let's call this noise. It's annoying. It's mad about it's like got a namespace collision or something. And then let's console read line. So let's see what kind of values. So those actually look pretty good. Okay, those look pretty good. Probably what we really want is to move it from 0 to 1. Let me see if I do that. Yes. So what we'll do here is we'll do total is equal to total plus 1 divided by 2. This we're gonna be clear here about what we're doing. And this should actually bring it to yes within our 0 to 1 range. So you see those nice little values. 0.3, 0.4. So what we're going to do here is use that total. And we're going to set it on this bitmap. We're going to set pixel at X, Y. And what is color? What the hell is color? What is this? How do I make a new one? Oh, from ARGB. We'll do color dot from so all right, let's do this here. So we'll do, it's gonna be an int, and we're gonna floor these, I guess. So we'll do total times 255. Actually, we want to floor it. Do math floor. And we'll cast it back as an int. And our color will be red, green, blue. And actually, I'm thinking here, this is going to actually become white the higher up it is. If we want to flip it, we can do that. We can subtract it from 1. And then at this point, we want to save. And we'll just save it as noise PNG maybe. Yes, system.drawing.imaging.image format. I think we need PNG. Yeah, that's pretty awesome. So let's see what happens. I'm guessing this is going to be in like my output folder. It's going to be bin, debug. There it is. Does it have data in it? Heyo! Check us out. What's up? How's it going? Oh, hold on 1 second. Sheesh. Sorry, I woke up super dehydrated this morning. I had to get some water. Okay. So, here's what I want you to imagine. Like, this is a little bit different because right here, each pixel here is actually, I think we can open this in, see if we can do this. See what this does. It's going to write it out as well. Oops. Did it? Yep, there it is. Okay, cool. So here's what we'll do. Let's just include it for now so we can, whoops. We can open it in here. Hey! So let's see if I can. Zoom in here. What the hell? Click and drag. Oh, okay. So I wanted to get I wanted to get in here really close so that you could see, but so it's a little bit too close. So each one of these pixels, if you can imagine this as kind of a height map sort of thing. Yeah, I tried that as well. It doesn't. Oh, that does. You're right. It does. I use that all the time in the browser. I don't know why it wasn't intuitive to use it here, but you're right. That did work. Control and my mouse wheel works. So if you can imagine each one of these as the top of our terrain, right? So this is a block, this is a block, this is a block. Each pixel is a block from the top, right? Now, if we did it that way, this is actually some pretty busy terrain, right? So it's like, I mean, it's moving everywhere. But as you can see, it uses that gradient function, so you actually get like everything's kind of smoothed out. You don't get just random peaks right in the middle. Everything's like gradually moving up. Now, if you remember, we had some of these things that we could change. So it's actually pretty interesting here because these are actually really small. So like we had that web page pulled up that had some pretty decent looking values. This is it. So this one has an amplitude of 64 and a frequency of 8. So let's try that. 64. I kind of am under the impression that this is not going to be what we think it is, but let's see. And actually, we don't even need this read line because we can just make it quit when it's done. Oops. And let's open our noise again. Well, see, I wonder if this is the same. So it doesn't look any different. So I wonder if we have to like, I wonder if we got to delete this guy. Oh, let's do it down here. Annie, you will get kicked out of here in a hurry if you act like that. So let's do if file exists 1 2 noise. Hold on. Hey. Come on. These dogs, man, I swear. These dogs, all they want to do is annoy the shit out of me all day. File, delete, path. So if that path exists, we'll just delete it, then we'll write a new one and see what happens. Value 1720. Wow. Yikes. So what happened there? We're getting some massive values. I thought this would constrain it though. No, because we're adding. Actually, I think this needs to be 1 divided by, I think this needs to be 1 divided by octaves. I think this is what we have to do here. I could be wrong. Yeah, I'm still getting a higher than. I need to constrain this value. So this is like a summation. See, this is really what's happening is this value is between 1 and 1 over octave. What does that even mean? I don't even know what that means. One over octave, and then we're multiplying by this amplitude, and the amplitude is what's giving us pain. I'm about to slap the crap out of this dog. The thing is, I don't know if there's I don't think there's a max, so we can't define like a proper range. Actually, yes, we can. Hold on. This is what we're going to do. Okay, so this needs to stay the same. Amplitude is going to be 64 divided by octaves, and 8 it's going to be divided by octaves as well. Negative 492. Whatever. We're going back to our original values then. I can't figure this out right now. But what we can do, this is going to keep it in between 1 and 0, I think, or 0 and 1. What we can do is scale it, and that's really what we want to do. Basically, there's no max. What we could do is find the max value and make it all relative to that. But we would have to do it twice. And nay, I'm not doing it twice. That's too expensive. I mean, this is already a shit ton of loops right here. But let me check this real fast. So let's just pretend that we want to scale this. So let's do float scale x, and let's just make it 2, and then float scale y 2.0f. Let's just give it these values, and what all we're going to do here is we're just going to multiply this by scale x and this by scale y. And this is going to give us basically a scaling for this pixel. And with that, it should be, well, it's still pretty busy here. In fact, that doesn't look nearly as nice. Why did I do this? Okay, you know what? This is actually, let's remove this for right now. Well, we can keep this, but let's just make it 1 to keep the scale even. This is what we're gonna do. What was it? What did I say that value was? Damn it. Amplitude 64, frequency 8. So let's give it amplitude 64.0f. This is what we're gonna do. And then 8. And then we're going to, I think what we want to do here is, in order to put this in the, we're going to do this. We're going to do, color is going to be equal to 0, which is going to be the minimum, plus, we'll do round, and it's going to be total times max times min. Why? Why am I not getting values between? Let's see, let's just see how high these values are getting. Because I don't think we don't need to save this anymore. Okay, so our values are like, they're getting pretty up there. Let me actually, let's do all this, and I'll just keep a tally of the max. Let's do a float max value equals 0, and then we'll say max value is equal to math dot, gotta do float math dot max, and we'll do max value, and it's gonna say I don't need this actually. Max value and total. Oops. And then down here we'll do console dot right line. Max is going to be max value, and then we'll do console dot read line to stop it from exiting immediately. So our max is 40. Max is 80. What I'm trying to figure out is What I'm trying to figure out is this. No significance to that value, by the way. What I'm going to try to do, this is going to be, I'm going to run this 1,000 times and see what the max is on 1,000 and see if it's anything like, so our first one was 80. This might take a while to run, actually. I can't wait anymore. Hold on. We'll do for 0, 1, 1,000, and then let's do a parallel loop. See if that. Well, is it not? I used the old school arrow. I use like a C++ arrow for my lambda. Derp. Oh, I can't do this. I can't do that. I can't do that because I've shared memory. I'm trying to take a sample, so it's not going to work. Let's just do it 100 times. This is slow as shit. $93 max. Why is this so slow? I mean, it is slow. $94. So here's what's weird about the scaling. I messed this up. The scale is actually supposed to be float sx is equal to, I think, 1.0f divided by width times scale x. Float sy equals 1.0f divided by height scale y. And then we can multiply these guys out. Sx sy. I think this is right. I need to get rid of this now. Just do this. Do you remember what our original value was? It was like 6, 7 or something like that. Sounds right to me. So we're getting good values. Let's go back to this. We're getting good values with this. So let's... Oh, I think I got rid of that. We don't care about that. Can save this. See what our noise looks like. Oh boy, that looks... Now we're talking here. Now we're cooking with gas. Okay, so this just looks like a straight up gradient, right? But this is more in line with terrain. But this is what we're going for right here. This level of smoothness. And all this is basically doing is this is the same noise function that we saw earlier, but scaled out. So let's actually do this too. Let's maybe reduce this to like 1.5. Maybe even less than that. So now let's see what it looks like. So it's getting a little bit more. Did I change any of the other values? No. So let's do like 1.1 maybe. Or it's not exactly like, it's not exactly what I was thinking, but all right, so here we go. Now we're getting more into like the cloud. This is more of our scale here, I think. Let's do like a 0.25 for both of these. All right, so now we're getting into like cloud level noise. So what we've basically done is instead of like, we're still doing per pixel evaluation, but the evaluation, instead of it being so condensed into, we're getting this more spread out. And this is what we're going to want, this type of, we're going to want this type of evaluation when we get into our terrain generation, because you don't want it to be so rigid. Because if you think about it, each block, if it's a meter or whatever, so we're getting into, actually, we've started, basically we built kind of the render pipeline and a camera and the basic building blocks of this thing. And we're going to start, sorry if you asked that a few minutes ago and I didn't see. We're starting to get into terrain generation and kind of the data structures involved in our voxels. And so we're actually getting started on building the terrain in the world today. This is like our first day, and we're starting with terrain, and we're going to use a noise function for at least the top or the height of the terrain. And so we're figuring out how exactly we're going to procedurally generate this thing. I will say that so far, I'm not really impressed with how slow this is. But I can't tell if it's... No, it's not the... So let's reduce like the octaves to like 2. See what happens. So it's just a little less defined. This is basically our anti-aliasing. Like the more we have, the more octaves, the like more defined of an image we get. Or the more defined of a... And really and truly, our octaves probably don't have to be super... high detail. They don't have to be super high detail. But this thing is kind of disgusting. I don't even understand why. I guess that's for the hashing. I don't know. Seems really slow. We might have to evaluate this later. Because like let's just take a general... let's do total milliseconds. And then let's console.readline. So let's just look at this. That's terrible. Oh, that's so bad. God, that is bad. So assuming... All right, that's a little bit better. It's kind of funny. Wait, that's not 16 by 16? Oh. It's not as bad, I guess. Yeah, there's 16 by 16. Okay. Well, let's add terrain. Let's actually move this noise in there. Let's remove this. Let's give this. I will probably at some point go through and make that better, because all of this is really, really gross. Now this is all upfront cost, so it's not really that big a deal. It may not be that expensive, like in terms of, because we are using a hash to look everything up. So in terms of the lookups for the gradient values and stuff, I'm pretty sure that it's probably fast, but I don't. It looks a little fishy to me. Care about this. This is what I needed to change. Terrain. Let's add just a. We'll just add terrain generator. And public. So I'm really tempted. I'm really, really, really tempted to create an integer vector 3, because it makes the math a lot easier. So for this, we want to pass in octaves. We'll do float frequency. We'll give it a default, and then we'll do float amplitude, and we'll give it a default of I don't think these things need to be. We'll make them read only for now. Uint, and then we'll do octaves. So what we're gonna do here is just we're gonna create basically a class that encapsulates that logic that we had before, and to basically generate our terrain. Eventually we'll have it return an actual chunk object. So we'll do octaves. We'll just give all these, we'll give them, I mean, to me this is fine to do all pretty general defaults. How are we going to do this now? Might be better to wait. Okay, so let's maybe start talking about, we got about an hour left. So let's move over a little bit. And let's start talking about maybe chunks and how we want to represent this. We'll come back to this. Actually, what we want to do probably is take our main. Let's go in here. Do we have? How do you? I could probably create some unit tests and use like in unit or something like that. Let's just move this little test, this dummy test in here. Let's just move this. Let's just move it into here. Excuse me. System.io, system.drawing, and I think we're good. We should probably make these int width, int height equals 512, and let's make sure these. Can I set these to incoming parameters? I didn't think so. Whatever. I don't think you can set them to read only either. Okay, we'll keep this there just for testing purposes. Let's go back to using our regular implementation. Let's make sure we're still running. Okay. Okay. So let's talk maybe about chunks. And maybe will this help if we... I was gonna pull up like paint or something, right? I don't know if it's gonna even be helpful, to be honest. Sometimes it'll help. If I could draw, it would actually be helpful, but I can't draw. So let's think how we want to do this. So basically, man, I really want to represent this in a way, but there's no way I'm going to be able to draw this. Maybe if I can. Wait, why is it? Oh, there we go. Hey-yo! I'm an artist. Get the fuck out of my way. Align. It might actually be easier for me, seriously, to program this versus like trying to draw it. So we have our voxel, our single cube, and these things are all one unit. And as we add these things, we need a way to represent entire volumes. So like currently, like this is what, a 3x3, but it's flat. So then we got to come out here and we got to add this and give it depth. So this is when the graphic starts to look really bad. But you get the point. And the thing about voxels that's neat is that, especially just cubical voxels, is that you kind of build just a bigger cube in a way. And so what we a kind of abstract approach to this would be to take, I guess, would be to take like representations at set sizes and allow them to continue forever, and figure out a very good way of like encoding things and decoding things such that the bigger thing becomes smaller detailed things, and those detailed things become smaller, even more detailed things. And then as you kind of navigate out from detailed to less detailed to less detailed to less detailed, you end up with these expanded versions. So where I might drill down and find that this block right here is made of stone, if I navigate out from that, I reach this larger structure that contains all the smaller ones, and maybe I can't see that that's stone from where I am in the navigation piece. So like when I say navigate, I mean think of it like a level of detail, sort of like a level of detail system. As you get closer to something, the details start to show up. And there's no point in showing super high-res detail from way far away. Same sort of concept here, but it's figuring out how to represent lots of small things with one larger thing. And then you can take that one larger thing and you can actually make it into a system of larger things, and that becomes a big thing. So in our system that we're going to do, it's not going to be completely abstract, but essentially what we're going to end up with is, what is this font? I'm excited to see what this font looks like. We have block. It's not as cool as the name makes it sound. We have block, which is going to be one of those, block, which is just going to be one of our original cubies. And then for here, we're going to have chunk. And if you're wondering, and the chunk's just going to be a lot of blocks. And we're going to figure out how many blocks. some of that depends on generation. Some of that depends on other limitations. How you want to break up the world depends on how much processing power you need to generate and stuff like that. So you have to kind of be, it's kind of like a little trial and error experiment. And the way we're going to handle these as you move out in your system, we're going to keep kind of a set area where these things can exist. So one more little small explanation here. So we'll keep that up for a second. And I'm going to actually save this because I do have a doc folder that I'm just trying to keep stuff in. Chunks. And so the other thing we want to talk about is, so when you have a system of chunks, we're going to think about this in like a top-down way. So this is going to be like, imagine this as looking down on top of a chunk. Now it's going to go down further, but we're just not going to see that. I think I need to, how did I do this last time? Select transparent. Okay, there. And then probably one more. We're going to have more in our top down. We're going to have more, you'll see, actually. I think it's important to kind of go through this visually because, well, at least for me it would be. I'm a fairly visual learner. And in fact, I think probably what we want to do here, this is not going to be exactly right, so I'm sorry. I tend to be a little bit of a perfectionist, but I don't want to waste a lot of time on this. I just want to draw the example and move on. Looks good, actually. Okay, so imagine these as our chunks, our larger chunk area. We're basically, and then hold on, let's. This is going to be imagine this is like like a blue or something. Wait, I thought that would color it in. Oh, there we go. So imagine this is like our player, if you can. Oh man, come on. Paint is so weird. So imagine this is our player. We're basically going to say, it's going to be a kind of a priority system, but we're basically going to say these chunks, oh, it would be nice if I could do that in the background, but it's probably not going to be able to do that. Let's select this green again. Yeah, no fill. Okay, I don't want to do fill. So we're going to say that the chunks like immediately surrounding the player are going to be, these are going to be high priority. And of course we have a high priority. And kind of without being, I mean, this is going to be fairly obvious, but this inner must load. basically, as a requirement, the chunk that the player exists on must always be there. And we can talk about what that actually means. It can be the physics. It can be the visual representation. I kind of tend to think of it as both the physics and the visual being there. But those of you who have played Minecraft, you can basically like run ahead and like if you fly up and then you run really fast, like you can beat the terrain loader. But it does something simple like this. As you move, it is constantly keeping track of what chunk you're on or where you're moving to, and it can prioritize and load specific chunks based on kind of where it's guessing you're going to be versus where you are. All of that information it can use to determine what order to generate or load chunks. And then we'll do this thing right here where we'll say, and these are loosely defined, by the way. This is not like any sort of, we have to do it like at this specific dimensions or anything like that. But these out here at this level, we will say lowest priority and max. So basically these blue ones in the outside of these would represent if you just were standing still, your player was standing still, of course this red one would be loaded and these green ones would load in as fast as possible unless you're moving. Like when you're moving, we will continually like take where you are and determine what else should we load. We can also determine what to unload. So imagine this. So these out here, these chunks out here, since they're not in this max visibility range, they would actually not be loaded. So what we're kind of trying to say is the closest one in, we need to keep it loaded. It needs to always be loaded before the player can even move. If that means stopping the player, then that's what we'll have to do. Hopefully we'll be able to get terrain generation and loading fast enough to where that won't be a problem. Once this one is in, all of these need to be in. And imagine this is top down, but think of it like because we're in three-dimensional space, there's also above and below chunks as well that will be basically stacked on top. It's like the ground, the underneath, the caves, whatever else you want to imagine there. Those are part of this. And this actually what we're looking at is kind of a sphere around our player. And as we move, that sphere follows us. And as things come in the sphere, we load them, but we kind of do it from an inside out way. And then also, though, there's like a buffer. There's like a inner sphere that's going to be this high priority. And then there's like this giant outer sphere. It's like as we move, this blue, it's like, so let's say we're here and we move here, this blue would still keep this chunk loaded because it's still part of that max visibility range. So really more, it's like this rather than a square. However, this is kind of the point, because our circle here includes this chunk, or a very small part of it, it's going to load this chunk. So you end up with kind of a square looking, sometimes it's missing corners, whatever. But the point is basically as you move away, this thing right here goes away. So, oh, hey, Mary Tyler. So what's the plan?
I'm going to my appointment. Jordy will be back home in like 15 minutes. I dropped the ball on something. I keep thinking that I've talked to you about it, and I don't think I've talked to you about it in like a month. Here, baby. And
What is it?
Dad's thing in Hilton Head, which was the reason that we canceled the trip with Tree.
You don't want me to go.
No, I don't want you to go unless you want to go, but I wouldn't be back till the middle of the day on Father's Day, and you'd be here with the kids by yourself on Father's Day.
It's okay.
He wants a baby.
We'll talk later. A baby, like a human baby?
I said, you and Daddy both.
Okay. We can talk about it later. Just let me think about it.
I know.
I'm in the
would
middle
have
of
to get
stuff.
Connie. Okay, Antonia's gone now, so she can come whenever, whatever. She has her car. But I would be leaving Friday night and be back Sunday afternoon.
Okay. Let me think about it. Do you want me to come? Is that ultimately what you want me
You
to do?
don't have to come. We would have to pay Connie a lot more if you come. But I also don't want you to feel like you're just
I don't
stuck with the kids on Father's Day weekend.
I don't need anything for
Because
Father's Day.
if you come and if Janie ends up coming, we would have to get a whole other room and properly split it. But
Okay.
right now, Dad has a suite that has a pull-out couch that me and Tyler could sleep
Okay.
on.
Well, yeah, we'll talk about it later. I just gotta think. Okay, we're good. It's not a big deal. It's not that much of a drop of a ball.
I know, but I just forgot about it, and Janie just texted me and was like, Tyler thought I had to work this weekend, but I don't, so when are y'all leaving for Hilton Head? And I was like, I was thinking it was next week. Like, I just got completely blindsided.
That's okay.
She's going to be good. Jordan's going to text you when she gets here.
Okay.
I love you, baby. Hey, when Jordy does get here, just take that inside to your bed and rest for a while because you woke up real early this morning, okay? Okay, love you.
Anyways, sorry about that. Family business. Yeah, OBGL bindings and CSharp. So, where are we now? So, okay, so we have these ridiculous looking graphics, and I'm going to save both of these because I know they're ugly, but for me here, they're actually pretty decent.
Daddy, is there any drinks upstairs?
No, we don't have any.
I'm thirsty.
You could grab that water bottle right there and have some of that, but that's about it. No,
Start grabbing those cups up here.
yeah. I'll give you a link. This. Oops. It's very basic, and it provides all the bindings we need. So it doesn't try to build like an engine on top of, it just is a really good, it's got math and it's got like SDL support kind of wrapped in it, and it's nice. I like it a lot. Also, the developer who built it or who wrote it was building a Voxel engine as well, and it looked like it was supporting very easily everything he was doing, and so it made the decision pretty easy. I don't need a full on like 3D engine to do this. In fact, I think that cuts out some of the importance of kind of what I've wanted to like, work through. So I didn't go that route. Once we go later, if we look and we want to create like a DirectX render or something like that, we can. But very simply, I mean, this is really all we need. So let's build maybe a chunk. And let's put it at, let's call, well, we can probably call it Voxel. So we need a few things. We need to create a block first, a block object. Now, blocks is kind of, I'm a little bit on the fence about this right now, but because I think we can make this a value type. Oops. Didn't give it a good name. We're going to do a couple things, actually. So let's make a enumeration as well. We'll call this like block type. And fix up the namespace here. So let's do, this is going to be public and block type. Now, I think immediately it's fairly easy to assume block type is a byte, right? But that kind of limits you. So I almost want to say, let's make it a short. I don't think we will create 255 different block types. $256. Basically, that's like a 16 by 16 16 by 16 texture map or texture atlas or whatever. This used to just be called a sprite sheet. I just feel like byte's limiting. I just feel like byte is limiting here. I mean, granted, yeah, it's half the size of a short. All right, you know what? Let's just make it a byte. I don't care. Let's make it a byte. And let's just start with some basic types here. I'm going to do air as the obvious one. Dirt, right? What are some other ones? Wood.
Now that I'm done with my bean, I let my seed play with the cup. And I use leather.
Excuse me.
Yeah, she loves it.
Does she?
And I use leather like to smooth the extra clean. Hey, Daddy.
Yes, ma'am.
When they're next time we're gonna go to the fair because my Hello Kitty shirt made from the fair has stains on it and I need a new one.
We'll get you a new one next time.
I don't know when we're gonna go because it's almost summer.
Well, I don't think the fair is open right now. Well, Okay. So I just wanted to make a note here. Basically, you're just saying we're going to leave this as a byte, just to keep it super short and simple, just for the purposes here. But it's important to realize that if this was a real world problem and we wanted to build a game that had more than 255 types, we would need to somehow be able to support kind of this extendable system of types. So I just make a note here that we are aware, very aware that we're limiting ourselves here. I think we want this to be a value type for now. And I also think that vector 3, can I select? Oh, weird. Okay, well. Why is it saying that it? Okay. Okay, that's also a value type, so that's good. Here's the thing: it's like I want to. Am I crazy? Am I crazy that I want to use it? I want to write a version of vector 3 that just contains ints. In terms of storage, it's the same as a float. But in terms of the math, it's stupid fast. Like integer math is fast. So am I crazy that I want to do that? Because we're using cubical voxels, where they're all 1 by 1 by 1. I mean, am I crazy that I want to set position as an integer? It seems like a no-brainer. Or is it really saving me that much? I can't. I just don't. I start thinking about how we can easily use like bit masks and other like little bit level, bitwise transformations to convert from like block space to chunk space to world space, whatever. Maybe we'll do that. Maybe we'll do that later. Okay, so let's think about what all is this block. What all does this block have? I mean, I'm going to go about it in probably the most straightforward and simple way. And then if we need new things, we will address it. But I'm going to build this exactly as if I was doing it from scratch, even though I have my little prototype that I wrote over here. The prototype clearly has holes in it in terms of implementation, just because I prototyped it as quickly as possible so that I could start streaming like this. So I think this basic level here, we just do we just need a position? We do. We just need I guess we want to call it a local coordinate. I normally say it's really important to use encapsulation, but since we're a value type here, 1 second. Give me a second, guys. Okay, here. Jordy's back.
Hey, look how cute this goes together.
I know it is. It's cute. Come
I
on.
think Twyla got me this.
She did?
Yeah, and I took the tag off. More warm. And I'm gonna use that little bowl up here so my sheep can play with it. Ah!
Okay. Sorry about that. Had to take her out to the babysitter. See, this is why. Because this is an int. This is a 3i. And actually, well, you know, I think GPUs nowadays are completely optimized for floating point. So it's not really, I don't think that we would gain much from uploading ints instead of floats. Now, if we were to make this shorts, you know, clearly we're cutting our data in half. However, that can be a lot more limiting than like the block type. I think we're a lot more likely to start exceeding shorts than we in terms of world coordinates. So let's actually call this world. Because what I was thinking about doing is, at first I was thinking, well, we'll just have each block be able to run a conversion, a local to, but I don't like that. Actually, I think that what we're going to end up wanting to do is just when we generate our chunks, we can just assign both of these. Because the blocks don't really change. Yep. So you have kind of piqued my interest in terms of larger chunk sizes, because I've always done just 16 by 16 by 16 chunk sizes. The prototype that I have right here is 16 by 16 by 16. For the block, we will make, the only thing that we will have on here that will be read only basically is going to be this block type, and we're going to call it block type, and we're going to have whoops. We'll have a get and a private setter. However, interesting. I guess what I'm thinking of is I think at that point we would just remove the block. We wouldn't actually change its type. So I think this is right. The type of block. And then world position, that's fine. We'll just leave that there. The only reason we'd want to have a local position, the local position would be the position within the chunk that the block exists. And the only reason we would want to have that is just to reduce the amount of time we spend basically querying what local coordinate are you? What local coordinate are you? Over and over, we just assign one when it's generated or when it's loaded, and then we just don't have to worry about it from there on out. You have to have, so the only rule to structs or value types in C# is they have to have a default constructor. So we'll have our default constructor here, and we will just basically pass it a block type air. So and block type, and we'll say block type equals block type. Why is it angry? Wow, okay, never mind. They can't contain? What? I need to read. This is bad. Let's see. I don't remember any of this. C# structs. What are the rules? What are the rules? That looks fine. So you can't have an explicit default. But why is it mad about this? Oh, I need to. I guess I need to set the type and the position. Man, I don't like that. I guess. Okay. Clearly, I'm not getting it here. Okay. That fixes it. So you can't have default constructors. That's completely the opposite of what I was thinking. I thought you absolutely had to have a default constructor because it's a value type. It's very odd to me. Is this really true? I guess it is, man. Weird. And I suppose for right now, I think that's all we're gonna need. We might want to define some operators. I'm pretty sure. So let's do a couple things. I want to I really want to generate. How do we do this? I really want to generate Can we not have it? That's annoying. Why doesn't it have that? I just want to generate like hash field and equals and that crap. I don't like this. What's a I need a good hash function. What's a good hash function? Maybe I can just use the vector3 hash. I wonder if it's good. That looks probably pretty decent. Did you ever consider generating the mesh on the GPU as well? It might be weird to think about, but basically you'd have a compute shader generating terrain, passing data to a compute shader that would generate the mesh data, which you would then turn around and pass it through the normal GPU rendering pipeline. Sure, like, did you ever?
Come on, kill me, I'm here!
Actually, let's see. Value type equals. My kids are nuts, man. Yeah. Well, we were trying to do value type here, so let's public override. Well, okay. Equals. It's not much of it equals. Basically, how would you do this? So var block equals, because we can't cast it. Will we have to hard cast it like that? Oh, we can actually check for that. So if null equals object, or like get type not equal to get type. This seems really expensive. Maybe it's not. And at this point, we just really want to return is equal to block. We know that at this point it's the same, and we're gonna return block type equals block type and world dot. I wonder if you can do approximately. That's only for What about override? What do we need? Hash code? I'm gonna. Oh, we need a good hash code. How do we generate? Just 1 second, please. Okay. And from what I did remember that you had. Okay, so hold on. You made a post. Explain. Okay, I see what you mean. So it got a little bit deep. It got a little bit too deep. So let's do this. Public bool equals and we'll do block. This is a little bit easier to do because you can do stuff like this, like return block type equals our block type and block.world equals world. I really want an approximation comparator there, and I think for right here what we need is this. We want to use reference equals null and object. Oops. Return false. And then here we want to return obj is block and equals block obj. There. That's a lot better than comparing types, even though maybe maybe the compiler just generates the same thing. Our hash code, let's just use we'll make this unchecked, and we'll just return we'll return the world coordinate, hash code, and XOR. No, let's multiply it by, like, what's a good, hold on, I have some prime numbers. That's 397. I think that's prime. And then we'll XOR it with the int value of block type. That should give us a pretty good hash value. We can run a test on it later. Oh, I'm in South Carolina, in the U.S. Can you tell? My accent's a little twangy. Not intentionally. Quality for block type. Okay. And then we wanna override also operators. So let's do public static operator equal, I believe, and you can do. Is that how you do it? Oh, bool. Operator equal, and then we can do block left, block right, and then what is it mad about? Oh, okay. It wants me to also define a not equals, but I think this is a stupid. This is equal. This is as easy as this, and then public static bool operator not equals. Left, block, right, return, and then not equals. Left equals right. Okay. Inequality operator and inequality operator. And let me find a. Let's read it. It basically just suppresses any sort of overflow check for constants or for numerical types. So if the expression produces a value that is outside of the range of the destination type, the overflow is not flagged. For example, because the calculation of the following example is performed in an unchecked block or expression, the fact that the result is too large for an integer is ignored, and int1 is assigned the value of negative whatever, blah, 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 blah. Basically, it overflows it. It just changes it into a C++ primitive. So I think what normally would happen here without unchecked, you would actually get a arithmetic overflow exception. Why do we want this? Because when you have anything that checks overflow and then throws an exception, it does way more work than we want it to do. We don't want every single time. If we start using blocks as keys in a set, which we will probably, we want very fast lookups, which is what the get hash code will be used for. And we don't want it to take a long time. We don't want, I mean, if we're calling it a lot, yeah, basically just loops back to the minimum value. But the point is that it doesn't add, the compiler doesn't generate checking for overflow. And because what would happen is if we left that as a check statement, a normal statement, then every single time we executed some sort of arithmetic, or every time we wanted to generate that hash code, it would be checking to see if it was overflowed or not. We just don't really care. Like if it starts overflowing, then it starts overflowing. I get the impression that it's probably going to be pretty hard to do that, but it's, you know, again, we're limited to an int, so that's fine though, because really the hashing, we just really want the bit implement, like we want the bits to stay the same. So if it overflows, we're still going to probably get a unique value from it. I did want to see to make sure here that he has a fairly reasonable, oh shit. He doesn't. Wait, are we, if not use numerics? Wait, what does that mean? Oh, he's going to eventually swap these out, I guess? Oh, okay, I see. He's made his API compatible with vector3 from system.numerics. And I think he's basically changing it so that he'll be able to swap these out. However, that's not a good hash at all. So it sounds like what we'd end up having to do really is oh, that only works with positive numbers. I'm going to have to look into this. I think this is actually pretty difficult to do, such that it's unique. So we might actually end up having to just store them in a 3D array versus using some sort of hash. I mean, in the end, it's the same thing. So we'll just try to be clever. I mean, we can leave this for now, but I actually think this is going to cause collisions with because of the lack of hash function this has. Anyway, doesn't matter. Where are we? I got 4 minutes, so we haven't made it very far. Sorry, I got caught up on some of I mean, these are important things, right? I mean, equality and stuff like that. Because it's a value type, it's going to have copies, right? These things exist on the stack most of the time. Sometimes they can get promoted to value types in odd circumstances, like when they have to be captured, like on lambdas and stuff. There's certain rules that the runtime and the compiler will promote certain value types to reference types, and it's not always as easy as looking at it and say, yeah, that's when it does that. At least I couldn't recite that at all. So kind of just to kind of revisit what we're going to do here is our world generation is basically going to generate these blocks. And as it generates these blocks in a set dimension, like let's just say 16 by 16 by 16, it's going to pump them into another container, a 3-dimensional container, which is going to be in our awesome documentation that we have here. Our chunk. And then we're going to lay our chunks out kind of like this. This is a top view. And our chunks are kind of going to be in the priority. It's starting at the center of where our player is, and it's going to kind of bloom outwards. With a focus, I think, on the same plane as the player, or around the same plane as the player. That's going to depend. I haven't really concluded that yet. Here's our draft pipeline. That actually looks pretty good too. So getting this stuff is important because equality matters, because we're not using reference types. We're going to have copies of this stuff. So we need, our equality needs to not look at anything to do with memory location, right? What reference equals is gonna compare memory location. We want to actually check. We want to compare whether or not block type is the same and world coordinate are the same. If those two are the same, then we're calling them equal. It doesn't matter if they live in completely different spots in memory. So we've kind of laid this basic structure. What we're going to do next is we're going to use a chunk. And I'm pretty sure that I know CSharp has support for types like this. I have to look at this and actually understand the semantics of this notation. But so you have a regular int or a regular int array. We'll just call this like I array, and then you also have a 2D array, which I think you have to I2 array, and then you have int. You have a 3 array, and then you also have these. So this will be, you have this 2 or array 2D, and you also have this array 3D. So I'll be honest, I don't know what this is. I don't know semantically what the difference is between this and this. But I would guess there is one. And then there's the approach like this, where you can use a single 1D array, and you can do x plus y times width plus z times width times height. Sounds kind of crazy, huh? But this actually will create a linear indexing given an x and a y and a z. This would give you an exact index. So there are lots of ways to do this. This is actually pretty efficient, and it's stored linearly in memory, so it's fast. I'm not sure what this is. I have to really study this because it's been a while since I've written any C#, and this is fairly new to me. I think I'm not sure. I'm not even sure. But I will look at this on my own time, and I will follow up with, because we can represent these blocks in a number of ways. But really, what we want to make sure is that the garbage collection isn't churning, because we don't necessarily want to. This is already kind of a micro optimization, but we're looking at it. We have to look at it this way because we're going to be dealing with a ton of this data. And so it's important that we consider each step very carefully. We don't want things to be necessarily random access. And what that really means is that we have memory allocated here and we have memory allocated here. Well, when you're using a container, sometimes the data inside that list or whatever can exist here and here and here and here and here. And as we go to fetch data from memory, it has to keep jumping all around. And memory is a lot easier to fetch when it's close to where it was. So if it's a linear allocation and we're just extracting things off the heap, it's much faster. And you don't and then also garbage collection wise, it doesn't have to like find each heap allocation that it's normally. These things are really good about allocations and tracking them and figuring out how to best clean it up when it's done and that sort of stuff. So it still is kind of a micro optimization, but it also does matter, especially when you're dealing with lots of data. So it's something we want to consider. I mean, clearly an int array, just a 1D int array, is going to create a big old long string of linearly allocated block types. I'm not sure about these. Same with this, though. I think for the most part, you're getting, and maybe not though, because you would have to allocate each one of these as you're creating it, versus this, you've only created it once, and it's this huge chunk of memory, and then you can use this indexing, and it's actually super fast. So we may use this, and we may actually wrap this in something that looks like this. But I'm not sure, because I really have to research what this is. This might actually be the same thing as this, and if that's the case, then we'll just use that. Anyway, if anybody got any information about that, please let me know. I'm going to study it on my own time, but I have to go. I'm sorry I'm talking so fast. I got a meeting that I got to get on in just a few minutes, and hopefully I'll be back tomorrow. We can start on the chunk stuff. We can start on generation. We can start on displaying some of this stuff and generating the meshes. We're on our way. So we're going to start this stuff, and we're going to start cranking some of it out. Anyway, thank you guys for hanging out again this morning. I appreciate it. Thanks for being a little bit patient. I'm moving snail's pace kind of, and I'm talking a lot. So thanks for being patient. Thanks for hanging out. Don't be afraid to ask any questions. Share, talk, contribute, whatever you want. That's kind of the point of this whole thing. So anyway, thanks again. Talk to you guys soon.